Hello all, welcome to this video on Networking Lab. Today I'll be talking about the implementation of distance vector and link state routing using ns2. We'll begin by looking into an instance procedure in ns2 called rtproto. Now this instance procedure in the simulator, whose path is given here, specifies the Unicast routing protocol to be used in the simulation. It takes multiple arguments, the first of which is mandatory. This first argument identifies the routing protocol to be used. Subsequent arguments specify the nodes that will run the instance of this protocol. Now, the default is to run the same routing protocol on all the nodes present in the topology. Now, this is the format ns rtproto dv n1 n2 and n3. This means that the distance vector algorithm will be run, that is the DV agents will be run on the nodes N1, N2 and N3. Similarly, to run link state routing on the specified nodes, this is the format ns rtproto ls N1, N2. If more nodes are present, they are also specified as such. If a simulation script does not specify any rtproto command, then ns will run static routing on all the nodes in the topology. Multiple rtproto lines for the same or different routing protocols can occur in a simulation script. However, a simulation cannot use both the centralized routing mechanisms such as a static or session routing and detailed dynamic routing protocols such as distance vector. Now we'll see how to set up routing. So we'll begin by looking into unicast routing. Now the format for unicast routing specification is ns, rtproto and the type. Now the different types available here are static, session, distance vector, cost and multipath. We'll see what a few of these are. We'll begin with static routing. Now the static route computation strategy is the default route computation mechanism in ns. This strategy uses the Dijkstra's all pairs SPF algorithm, which is present in the following path. The route computation algorithm is run exactly once prior to the start of the simulation. The routes are computed using an adjacency matrix and link cost of all the links in the topology. Now we'll see session routing. Now this is almost identical to static routing in that it runs the Dijkstra all pairs SPF algorithm prior to the start of the simulation using the adjacency matrix and link cost of all the links in the topology. However, it will also run the same algorithm to recompute routes in the event that the topology changes during the course of a simulation. In other words, route recomputation and recovery is done instantaneously and there will be not transient routing outage as in case of static routing. Session routing provides complete and instantaneous routing changes in the presence of topology dynamics. If the topology is always connected, there is end-to-end connectivity at all times during the course of the simulation. Now we'll see DV routing or distance vector routing. Now this is the implementation of distributed Bellman-Ford routing in NS. Its implementation sends periodic route updates every advert interval. Now advert interval is a variable which is a class variable in this following path. Its default value is 2 seconds. In addition to periodic updates, each agent also sends triggered updates. It does this whenever the forwarding tables in the node change. This occurs either due to the changes in the topology or because an agent at the node received a route update and recomputed and installed new routes. Each agent employs the split horizon with poisoned reverse mechanisms to advertise its routes to adjacent peers. Split horizon is the mechanism by which an agent will not advertise the route to a destination out of the interface that it is using to reach that destination. In a split horizon with poisoned reverse mechanism, The agent will advertise that route out of that interface with a metric of infinity. Now we'll see multicast routing. Now the format is ns multicast. Now the statement will be given immediately after the new simulator object is created. And this is how to specify the type ns rtproto. The types available are centralized multicast, dense mode, shared tree, and bidirectional shared tree. Now some of the other types of routing supported here are source routing and hierarchical routing. We'll begin by looking into centralized multicast. The centralized multicast is a sparse mode implementation of multicast which is similar to pim-sm. Now pim-sm is protocol independent multicast sparse mode. This is a protocol for efficiently routing the IP packets to multicast groups that may span wide area and inter-domain internets. A rendezvous point or RP routed shared tree is built for a multicast group. The actual sending of prune, join messages, etc. to set up states at the nodes is not simulated here. A centralized computation agent is used to compute the forwarding trees and set up multicast forwarding state S, G at the relevant nodes as new receivers join a group. Data packets from the senders to a group are unicast to the rendezvous point. Note that data packets from the senders are unicast to the rendezvous point even if there are no receivers for the group. Then there is dense mode. Now this is an implementation of a dense mode like protocol. Depending on the value of DM class variable, which is cache miss mode, it can run in one of the two modes. If this cache miss mode is set to PIM-DM, like forwarding rules will be used. Alternatively, cache miss mode can be set to DVMRP, which is distance vector multicast routing protocol. Now this takes the routing decision based upon the source address of the packet. The main difference between these two modes is that DVMRP maintains a parent-child relationship among nodes to reduce the number of links over which data packets are broadcast. The implementation works on point-to-point links as well as LANs and adapt to the network dynamics when links are going up and down. Then there is shared tree mode, which is a simplified sparse mode of a shared tree multicast protocol. Here also we have a class variable array which is the rendezvous point RP. Now this is indexed by group which determines which node is the rendezvous point for a particular group whose format is given here, the index and the rendezvous point. Now this is the format for specifying this ns rtproto st. At the time the multicast simulation is started, the protocol will create and install encapsulator objects at the nodes that have multicast senders, decapsulator objects at the rendezvous points and connect them. To join a group, a node sends a graphed message towards the rendezvous point of the group. To leave a group, it sends a prune message. The protocol currently does not support dynamic changes and LANs. Next is bidirectional shared tree mode. Now this is an experimental version of the bidirectional shared tree protocol. As in shared tree mode, rendezvous points must be configured manually by using the class array RP. The protocol does not support dynamic changes and LANs. Now we look into hierarchical routing. Now this was mainly devised among other things to reduce memory requirements of simulations over very large topologies. A topology is broken down into several layers of hierarchy, thus downsizing the routing table. The table size is reduced from n square for flat routing to about log n for hierarchical routing. However, some overhead costs result as number of hierarchy levels are increased. Optimum results were found for 3 levels of hierarchy and the current NS implementation supports up to maximum of 3 levels of hierarchical routing. Now we will look into DVR implementation in ns2. To implement distance vector routing in ns2, we can utilize DSDV, which is Destination Sequenced Distance Vector Routing Protocol, which is a standard distance vector protocol existing in ns2. It depends on the classic Bellman-Ford distance vector algorithm, and it occasionally updates routing tables with the distances to all the other nodes in the network. For more details on distance vector routing protocol, you can refer a previous video I did on the same in the playlist. Next is link state routing. Now to implement this, ns2 has included a routing protocol in which every router has comprehensive knowledge of the network topology. This router structures a map of the whole network and uses this data to establish the shortest path to each node. Generally known instance of a link state routing protocol is OSPF, which is Open Shortest Path First. Whereas the simulator ns2 does not have a built-in OSPF protocol, we can execute a simple link state routing behavior by changing the routing logic or simulating the link state updates using ns2's existing frameworks. Now we'll see a few details on the network dynamics, especially the link failures. Now there are some hooks in routing module to reflect such routing changes. Now there are 4 models available. The first one being a trace model where we have ns, rt model, the term trace followed by the configuration file name and the nodes affected by it. The second one is an exponential on or off mode where we have ns, rt model, exponential followed by the parameters and the nodes affected by it. Then there is the deterministic model where we have a few parameters and the nodes affected by it. Then we have rtmodel-at where we specify the time and the status of the link up or down and the nodes which are part of the link. Now the parameter list here can contain the start time, the time for which the link is up, the time interval for which the link is down, and the finish time. Now these are some of the examples of exponential, trace and deterministic models here. Now these procedures will require at least 3 arguments each. The first 2 arguments will define the model that will be used and the parameters to configure the model. The currently implemented models here are exponential, trace and deterministic. The number, format and interpretation of the configuration parameters is specific to the particular model. Now here in exponential, we see we had this parameter list where we had the start, up interval, down interval and finish. Now the start time in a default case for exponential is 0.5 seconds from the start of the simulation. Finish time defaults to the end of the simulation. Up interval and down interval will specify the mean of the exponential distribution, defining the time that the node or link will be up and down respectively. The default up and down interval values are 10 seconds and 1 second respectively. Now if any of the values specified by hyphen, meaning they are default to the original value. Now in deterministic model, it is similar to the exponential model except that the interpretation of up and down interval will be different. The up interval and down interval will specify the exact duration that the node or link will be up and down respectively. The default values for these parameters are the start time being 0.5 seconds from the start of simulation, up interval being 2 seconds, down interval 1 second and finish time being the duration of the simulation. Now the trace driven model takes one parameter, that is the name of the trace file. The format of the input trace file is identical to that of the output by the dynamics trace modules. So the format will be something like V followed by the time and the link operation, which is either up or down, then the nodes affected by it. Now the lines that do not correspond to the node or link specified are usually ignored. Now this is an example of that. The manual one-shot model will take two parameters, that is the operation to be performed and the time that it is to be performed. Now the rest of the arguments to the RT model procedure define the node or link that the model will be applied to. If only one node is specified, it is assumed that the node will be failing. This is modeled by making the links incident on the node to fail. Now if two nodes are specified, then the command assumes that two are adjacent to each other and the model is applied to the link that is incident on these two nodes. If more than two nodes are specified, only the first are considered and the subsequent arguments are ignored. Now the instance procedure rtmodel-at specified in this path. It is a special interface to the manual model of network dynamics. The routine RT model creates an instance of the appropriate type, defines the node or link that the model will operate upon, configure the model and possibly enable tracing. The command takes the time, operation and node or link as arguments and apply the operation to the node or link at the specified time. Some of the examples of this command is given here. The ns rtmodel-at, the time, whether it's up or down, and this is a node failure. These two are not being activated and deactivated, enabled and disabled. This is being a link being activated between N3 and N5 nodes. This is the code for the TCL script that I have used in this video for implementing distance vector routing. So to have an understanding of what ns2 is and how to write a basic code, kindly refer my previous video on the basics of ns2. Now the steps are the same. The program is almost the same as that I used in the previous video, where we create a simulator object, defining colors to the data flow, opening the nam trace file, writing the finish procedure, after that creating the nodes, etc. There might be changes in the capacity of the link and the propagation delay that have slightly changed, and the statements that I've added to this to show that this is distance vector routing is this. We have discussed this when we discussed on the theory part of this, that is adding the statement ns rtproto dv and then modeling the links to be enabled and disabled at certain times using the rtmodel-at statements. Now this is the sample screenshot of the output. You can see that the link here is red colored, which means it's down. So since it's down, all the packets that were passing through it are dropped. This is the output. And this is the network dynamics I talked about, which is a trace driven model. So there is V hyphen T, and the time at which it happened, the status of the link at that time, whether it's link down or link up, and the nodes that are incident there. So if there are more than two arguments, only the first ones are considered here. Similarly, there is the code for link state routing. Here also, to show that it's link state, the statement is added ns rtproto ls. Here also the capacity of the link and the propagation delay has been changed. Then finally the statements to enable and disable the links at specific times. This is a sample screenshot and the output. Here also we use the trace driven model to display the network dynamics. Now we will see a demo of how this code will be executed. Now this is the code for distance vector in TCL script. As I explained, these are the extra lines that were added. Link enable disable and the specification for distance vector routing. Then the script is run using the command ns distvector.tcl. Now here the packet size and interval is displayed. Now we have the NAM window open. Now here we'll adjust the size of the nodes accordingly and set the speed of the animation. And we start it. You can see packets passing. Source 1 gets an acknowledgement. Source 2 just sends the packets. You can see the packets were dropped. Now the link is down. Keeps on sending packets, but source 1 is not getting a response back. So they continue to send the packets. This is the timeline of what we specified. As per the script, the link is up again. Packets are being transferred as usual. Now these packets are dropped based on the drop tail technique as specified in the link specification. Now this was the trace driven model network dynamics I talked about. Each time there is a change in the status of the link that is recorded here. Now we'll see the code for link state. This is specified here, and the activation and deactivation of the link is also specified here. Packet size and interval is displayed. Then the animation window is open. We adjust the size and set the speed accordingly. And we start the animation. You can see that there is a difference in the capacity of the link and even the drop rate because I've changed it for link state. Link is down. Now the rate has changed as per the specification in the TCL script. Packets are dropped based on the drop tail specification given in the link specification. Here also we will have the trace driven network dynamics available in the console here. Any change in the status of the link will be recorded here. Now as a part of the output of this, a trace file and a NAM file will be generated. You can see a sample of what data is present here. Just a glimpse of how it looks. Further details on what these files and the fields are, I've explained it in the previous video on the basics of ns2. Kindly refer it for that. That's all for now. Thank you for watching.